to this computer. Okay, share it again. And there it is. Okay. Okay, thank you, Noah. We're recording now. So each of these pointers to the intrinsic call is of this type. And that type represents 4 floats. Okay, so if you keep that in mind, you should be able to figure out how to drive these parameters. Does anybody have any questions? Anybody? Okay, so you'll have no problems with project 4. Or is it 5? 5. No problems with project 5. Is anybody having problems with project 4? Okay, so I'm going to stop this, and instead, let's see what I have. I should very quickly be able to find the tutorial on. Okay, so very quickly, it's not there. Let's look in. It's not there. All right, let's look here. There it is. Okay, let me open this up. And share the screen. Make this get littler. Sure, I don't care. Open up I don't care. All right, so here is a tutorial on getopt. I have sent you the link. This is a repo that is public, so you can go ahead and grab that. And the tutorial program has a lot of comments in it. And these comments are, in fact, the tutorial. So getopt is an ancient Unix library. It does not exist for Windows. After all these years, who the hell knows why? There is a third-party open source version of getopt for Windows, and it is compatible with the real getopt. But of course, that is not a problem for you because at this point, you're familiar with the idea that you can be coding for the ARM on your Windows machine and get red lines. And that doesn't mean you're going to get red lines. You're going to get errors on the ARM machine. Has everybody got that? Okay. So why is there no getopt for Windows? Beats the heck out of me. We have been using command line programs. You've used them many times in your past here, starting in CS1. And what getopt does is it makes it easy to parse command line arguments. Now in Project 5, you're required to implement several. There's -S followed by a number, and -I followed by a number, and -H, which is not followed by anything. And that introduces the 2 different ways of how you can specify a command line argument. So I will go right down to the code. First, you have to include getopt. Okay. Then you're going to create a while loop. And the while loop is going to iterate over the command line arguments, giving getopt a chance to make sense of each one. Notice how this is constructed. While C gets the result of getopt, and while that's not equal to -1. So getopt is going to signify that it's finished with a -1. Now that has impact on how C is defined. It's defined as an integer. Okay? So characters will come in there, but remember that characters are just small integers, and a small integer can fit in a big integer. Okay, Davison, I don't believe I have you marked present. So let me do that. Is there anyone else who's arrived? That would be Kevin and Daniel. Are you either of you here? Okay. So did anybody have any questions about what I've said so far? So you're getting letters from getopt, but you have to treat that letter as an integer. At the end of getopt's processing, getopt will return -1. Okay. So if you, so in order to use getopt, you have to give it argc and you have to give it argv. You get those, of course, from main, which I have here somewhere. There it is. All right. And having given it argc and argv, you also tell it what letters you're interested in. So notice some of these letters are followed by a colon and some are not. If a letter is not followed by a colon, then getopt is only going to report to you its presence in the command line. So for example, -H. -H doesn't take any arguments. So it is H without, it's H without, stop that, it's H without a colon. So switch based upon the character you get back. Here's -H. Okay. All right. Contrast that with these others. Here's an F. That'll require another argument. I requires another argument. B does not. C does, and S does. So let's take a look at I. So if you specify -I, you're expected to give the -I option a parameter. And all of the parameters that go along with the arguments that have colons show up in opt-arg. That's an externally defined char star. So here, I is for integer in this trivial example. So I'm going to pass opt-arg to ASCII to integer, and that's how I capture an integer. Okay. Let's take a look next at B. B is how you capture a bool, and a bool is a yes or a no, no other argument going along with it. So no colon is necessary. Either the B is present or it's not. So you'll see that I have established a default value for the bool, which is overridden if the B option is genuinely there. Otherwise, the false remains. Okay. I believe I also set up a default value for the integer. Here is how you get a character. So this is not very common. So opt-arg is a char star. And I'm getting in the char. Now, you don't have to follow my methodology. You see how I structured this, where handle options is getting all everything passed to it by an argument. If you want to make these global variables, go right ahead. Global variables are not looked upon too favorably, but they're not looked upon too badly either. Okay, then capturing a string, I turned opt-arg into a C++ string, and capturing a float, similar to capturing an integer. Okay. Questions? So I described to you how you could set up a default value, which is overridden by the getopt handling code. Now, here's how you can implement a required option. Occasionally, some command line arguments are set to be required. And that is, for example, I set up the -s option to be required. And what I simply do is, after the while loop exits, I check to see if the C++ string has been filled in. So did its size, which began as 0, did its size end up being bigger than 0? And if false, it means the -s wasn't given. And in this demo program, I decided -s was required. Does anybody have any questions?
So if there were no required arguments, it would just be a void function then?
Correct. It could be. Okay. Yep. It could be a void function to handle your options if there were no optional ones. Another reason to make it non-void is, let's say you wanted an integer, and if the integer is given, so it is optional, the integer argument is given. If it's given, it has to be greater than 10 and less than 20. So you could implement that if statement in a function like this one and return a Boolean saying, go ahead and continue on running or not. One more reason to declare your option handling function as a bool or something else that has a return type is, for example, if you specify -h, I want the program to exit. So -h is only supposed to print the help and not run the whole program. So if I test your code, project 5, with -h, and it prints the help and then continues running, you get points off. Okay, does that answer your question?
Yeah, thank you.
Okay, does anybody else have questions about getopt?
Two questions. First, I'm assuming that getopt distinguishes between case, so lowercase h and uppercase h would be handled as two separate flags.
Correct.
And if we wanted them to be handled the same, we'd have to have the two separate cases.
Correct. Yeah, so you could just, as you see default, and dash H are together, you might have little h and big H together.
Okay. And then second thing, in your main on lines 36 and 37, you have function forward references, which is there a reason you put them in main instead of above it? I'm assuming it's valid they're there since you did that, but
Yeah, of course it's valid. And there are two schools of thought with respect to externs or even for variable declaration. As you know, in C++ and modern C, you can put a variable declaration anywhere in your code. The school of thought says you should put it as close as you can to where you are using it. Another school of thought says put it just in the function where you're using it, which is what I did here. And another school of thought says, put them up at the top. And all of those are valid. It's a matter of style. Pick one and stick to it.
so if you put the function references or the forward references inside of a function, are they scope limited to just within that function?
The forward reference is scope limited only to that function.
Okay, cool. Thank you.
All right. Any other questions? So one final thing to say about getopt is what you see here is a tutorial on the original getopt. There is a new, much fancier version that lets you have long options and short options. Like, for instance, it would accept both -H for help and, let's say, --HELP for help. That's not this version. This version only knows about the short options, the single letter options. Okay. I encourage you to learn how to use the newer version, because those long options allow you to make things easier to remember for the user. -H is a standard. That's not a problem for people to remember, but --help is, you can imagine, might be easier. Okay. Let me just check to see if I need to adjust any. Okay, so Kevin and Daniel, are you here? Okay, so you are forever marked as absent. Okay, anybody have any questions about getopt? Good. Okay. So why is Quark update the thing that is there? Okay, so let's close the workspace. And let's go back to our discussion on threading. Now, last time we saw, now where did we see that? Let me see, open a folder and buffet 3510. And I think it was pk-comp.org and P5. Yeah. Go away, go away. Okay. So we saw an example of using C++ threads. Okay. Does anybody have any questions about this example? Anything you'd like me to re-explain? Okay, further, we talked about what a thread is and how it differs from a process. To recap that discussion, separate processes do not share address spaces, whereas separate threads share one address space. Okay, does anybody have any questions about that?
I suppose
Okay.
this is maybe just a broader question about threads in general.
Yeah.
But if you have a thread that was, say, you put reading from disk onto a separate thread so it didn't hold up your main program, how would you, or something else, how would you move data from one thread to another?
Well, it's both a trivial question and a trivial answer, and also a very complex question and a complex answer. So the trivial part is all of the threads share the same address space, therefore they share memory. So for instance, you might pass a thread a pointer to a buffer, and then you could pass another thread the same pointer. And once the pointer has been filled in with data, the second thread could read it. So that's the easy part. The complex part is ensuring that the second thread can only read the data once the first thread has filled it in. So synchronization, the concept of threads is straightforward. Synchronization is the complex part of writing multi-threaded code. That's the part that will really trip you up, and it really forces discipline. And that's the part that we're going to talk about a little bit today in the remaining time. Okay? So mastering synchronization between threads is critical. You can't really use threading without it. And it's also where a lot of students run into mental brick walls. And the brick wall is created by your whole past history, where you were always able to assume that one instruction was executed after the other. So instruction 2 always executed after instruction 1. Instruction 3 always executed after instruction 2. Okay, so that assumption has been bedrock for you up until now, unless you've already taken the OS course, which some of you have. So that assumption, once you start multi-threading, no longer holds true. And that is because there's no way to predict when one thread will be yanked from the CPU and another thread will start. Okay? There's ways you can control it, but unless you're using one of those ways, there's no way to predict when you might be interrupted preemptively. And actually that's the scientific term is preemptive interruption. Okay. There is something called cooperative multi-threading, which the Macintosh, that's all you had on the Mac until OS 10. And OS 10 didn't come out until, in computer terms, I don't know, when did OS 10 come out? I'm sure Joey's looking it up right now. Prior to that, prior to OS 10, the Mac only offered cooperative multitasking, which was primitive Hell, the Commodore Amiga had it in 1986. And it took until when, Joey, for the Mac to get it?
OS 10 was released March 2001, first
Okay.
beta.
So Commodore did it in 1986. Apple did it in 2001. Yay, innovators, Apple. So cooperative multitasking means in order for one thread, for a second thread to run, actually, indeed, for any second program to run, the first thread or first program process had to willingly give up the CPU. If you had an infinite loop, your entire computer was frozen. Okay, got it? That's the origin of the spinning beach ball of death on the Mac. So cooperative multitasking is contrasted to preemptive multitasking. By the cooperative means that a thread or a process has to willingly yield the CPU, and that's actually one of the ways to do it is a system call called yield. That's a voluntary giving up of the CPU. Whereas preemptive multitasking is the operating system, for some reason, pauses you without your knowledge, takes you off the CPU, replaces you with somebody else, they run for a while, and at some point in the future, you don't know when, you get put back on the CPU. So that's preemptive. Okay. So the reasons that an operating system may yank you from the CPU include two principal ways. And even the third way I was going to say is a subset of the first. The first is you make a system call. Anytime you do a system call and you enter in front, you exit user land and go into kernel land, you're going to be removed from the CPU for some period of time. So every IO that you do that's not buffered, that actually causes a physical read or write, that's going to take you off the CPU, give somebody else a chance to run. The yield system call is another example. That would be the third way I was going to suggest, but you can see how it's a subset, special case of the first. The second way is that a timer goes off. So in a preemptive, in order to create a preemptive multitasking operating system, you have to have a timer. Okay, and I'll do a footnote because in OS, if I have a midterm or a final, one of the questions is a timer absolutely necessary? And the answer is wait till you take operating systems. But generally speaking, you have to have a timer, and the timer is reset once per quantum. A quantum is the period of time that the operating system will allow you to run a compute-bound process or thread. Compute-bound means you're busy executing without making a system call. So maybe you're in a for loop initializing memory. Okay. So that is being compute bound. Compute bound, once again, means that you're not making any system calls. So the quantum is the maximum amount of consecutive time that a process or thread is allowed to run when it's compute bound. Okay. In general, the length of the quantum in general is 10 milliseconds. So if all of your programs were compute bound, no one was doing any IO, no one was doing any system calls, the operating system would deschedule a task 100 times per second. So 100 times 10 is 1,000. So there are 110 millisecond quanta in 1 second. Okay. Now, why that number, 10 milliseconds? That's what was found to be empirically feel the best. If it was too short, if the quantum was made very small, what would happen? That's a question for you. Okay, if the quantum is too small, you know the answer to this. I guarantee it. So just say something. Okay, why have I been teaching you about a different way to structure loops that go through, like for loops that go through memory, for example? It's the same reason. Okay. I shall be very sad for the rest of the day. The reason why you don't want a quantum that's too short is if the quantum is very short, then the operating system will be spending a lot of time just doing the bookkeeping of switching from thread to thread or process to thread or thread to process, right? If it's too short, then the running tasks aren't getting enough of a time to do anything meaningful before being yanked off the CPU. Okay, so overhead is the reason you don't make it too short. What would happen if the quantum was too long?
You'd be letting various processes hog the CPU. So if you had a lot of processes running, it'd be taking forever to get back to one.
Correct. An issue of starvation, right? So if the quantum was chosen to be a number that's too big, the system would start feeling like it's not very responsive. So 10 milliseconds was a nice compromise. It's a Goldilocks value. It's not too hot, not too cold. Okay, and there are a lot of empirical values in computer science that are chosen for similar reasons, and they're all Goldilocks numbers. Okay. Okay. Now there is an exception to the too long and too short, and you'll learn about that in operating systems. There's one particularly commonly used means of doing CPU scheduling, which embraces the 10 millisecond quantum, as well as longer quanta than that. And when you take OS, you'll see why that is and how that works and why it's okay to do it that way. All right. So how many folks here, by show of hands, will I be seeing in OS in the fall? Okay. So a bunch of you, very good. I look forward to doing it. Okay, so it's now 2:16. Let's try writing an example to see where using C++ threading and see where this issue of synchronization starts to show its ugly head. Let's see. So I'll open a folder, maybe /temp. All right, just open that up. And now I can create a new file. So in order to use C++ threads, you've got to include thread, I think. Let me experiment.cpp and get rid of that. And okay, good. The squiggle went away, so I must have it right. There's going to be a worker that we're going to call. So in this case, we'll call it a void worker. And I want to give it a unsigned long pointer and an int count. And here's what I wanted to do. For int I equals 0 to while int I is less than count, I plus plus. Now we have not done this in class, right? We have not looked at threading in any detail prior to this. Okay, I'm just making sure because maybe I'm having a senior moment. Oops, I forgot the variable name. So I'm going to say star value plus plus. Okay, so what this is going to do, now this is already written correctly, but just for clarity, I'll put those parentheses in. What this is going to do, let's say we have a long, which is initialized to 0. And I call this thread with a value of 10,000. This is just going to add 10,000 to the thread. Sorry, to the value. Okay. And now let's do a main. Int main. Oh, what the hell? Let's include getopt. Getopt.h. Okay, that means I must have int argc and char star star argv. And int c while c equals get opt arg c arg v and I colon or c colon. And then go here, not equal to -1. And make there. Okay, let's add int count, and we'll give it a default value of 10. Okay. And now switch C. Case C, which is unfortunate, and it'll be count equals a to I of opt arg break. Okay. Just for good measure, I'll say default C error usage prog, I don't know what the name is, followed by an optional. So let's make that prog. I don't know what the name is. And then optional is -c with an integer. And del. And looks like I need IO stream now. And I also need using namespace std. And then I'll just exit from here. That's not a great thing to do, but I'll just do it. Okay. Anybody have any questions about the code so far? All right. Let's make use of code folding to get rid of that. I'm not interested in seeing it anymore. Okay. And thread star threads, and we'll go 4, which heck, I hate that. Let's say const int n threads equals 4. Let's make that n threads. Okay. For I is less than n threads, I plus plus, not particularly gorgeous code. So it'd be threads sub I equals new thread. And let's review what the calling signature is. Okay, I believe it's just going to be the name of our worker. And followed by an unsigned long pointer. So here's our unsigned long v equals 0. So it's been initialized. So address of v, and then followed by the count. All right, and then that launches all the threads for int I equals 0, I is less than n threads. Now we have to wait for the threads to complete. And that would be, we can wait for them in sequence, it doesn't matter. Okay, so that's going to wait for every thread to complete. Notice I'm assuming that every thread will complete. And if you look at the code, it should, right? Okay, so let's do some printouts. Expecting 4 times and that would be count or 4 times count. See out got v. Okay. What do you think? Anybody see any problems? So G++, what did I call this thing? Experiment. And that failed. Why? Why did it fail? It failed because threading is not part of the original C++. To get it, it was added at C++ 11. Ta-da. Okay, let's run this. Expecting 4 times 10 or 40, and I got 40. Woohoo! All right, let's try it with dash I of 100. Oh, I'm sorry, it's dash C. Look at that. Works. Let's go for 1,000. I got the wrong answer. We've not done this in class, right? Okay. I got the wrong answer. How the heck did that happen? Let me go back to 100. I got the right answer. Let me go back to 1,000. Not only did I get the wrong answer, I got a different wrong answer. And now I got the right answer. I got the wrong. I got the right. I got the different wrong. Different wrong. I got the right. God damn it, this is maddening, isn't it? Okay, welcome to multi-threading. Okay, if you thought debugging was hard in the past, but let me put it a different way, a way that makes sense for me, that resonates with me. If you thought debugging was fun in the past, debugging multi-threaded applications are much funner. Okay? In fact, I love debugging multi-threaded applications because they're really stimulating. Very, very challenging to find. And it's like, if you've enjoyed all the puzzles you've ever solved in CS before, these puzzles are going to get harder and even more satisfying when you solve them. Now, why are we having a problem? Sometimes. It has to do with preemptive multitasking.
Is it something to do with count?
Count is going to be safe. Count is going to be safe. Every thread of the 4 is going to get the same value, and every thread of the 4 is going to get a correct pointer to value. So that's not the issue. Okay, now let's put together our knowledge of assembly language. Let's bring in our knowledge of assembly language into this. So there's going to be some code like this, and I'll take some liberties. There'll be like a label that loads into, let's say, X0 from some pointer register. Okay, so somewhere I've got value. Okay, so clearly I'm taking liberties with assembly language. And then there's going to be an add of X0 to X0 and 1. I'm adding 1 to it. That's right here. And then there's going to be a store. Okay, so this code is in here somewhere. Do we agree? Okay, we agree. Now, notice that what looks like a single statement in C++ with our assembly language knowledge, we now know it is more than that. We know it's 3 instructions. In the past, we could always count on this instruction immediately following this instruction. And this instruction immediately following this instruction. So given that, does that give you any insight into what the problem is? Remember, you don't know when you're going to be yanked off the CPU.
So is it that multiple threads are loading the same value and then they're both storing the same value?
Okay, you've got a good insight there. Let's talk about that. The same value. Let's call this a resource. The resource is the memory location specified by the pointer to value. That is a shared resource. It's being shared amongst the threads. That is the source of danger. No matter what a resource is, maybe it's a variable, maybe it's a file, who knows what it is. If a resource is shared, access to the shared resource is where your multi-threaded bugs will creep in. If there are no shared resources, you can't have multi-threading bugs due to collisions of some kind. Of course, you're going to have different kinds of bugs, but you're used to those. So once again, this is the fundamental thing about writing bug-free multi-threaded code. If you have any kind of shared resource, you have to protect access to it. Okay, so Eric, that was a great observation. Now let's hammer it home. We only have a few minutes left. What about this shared resource is leading to trouble?
Can I take a stab in the dark?
Of course.
So if you execute that first line there, load the value into x0, and then you get pulled out, some other thread runs for a bit, it increments value more. When you get brought back in, you're going to get your registers restored exactly as they were, including the old, value of value. So you work off of that, and then when you restore back into it, you effectively erase the other thread's progress, but it thinks it's counted it. That other thread thinks it counted it. So that's why we're getting semi-random undercounts.
That's absolutely a perfect answer. So folks, let's say you're yanked off the CPU here. Or let's say, yank, right? That's fine. You completed one operation. But if instead you happen to be yanked off here or here, once again, you don't know when you're going to get yanked off the CPU. If you get yanked off after this instruction or after this instruction, in your internal state, as Joey mentioned, when you get back on the CPU, you are working with old data, which will then overwrite whatever changes another thread has made. Okay? Does anybody have any questions about that? You only got 5 more minutes. So why does it work sometimes? I told you why it fails. Why does it succeed? Let's try this. Let's do 10 works, 10 works, 10 works, 10 works, 10 works, 10 works, 10 works. It's totally reliable now. Let's go to worked, didn't work. Is it just because the number is bigger? What is that number influencing? Okay. So the reason why it appears to work when the number is small is because each thread, once started, gets in and out and completes its business before its quantum is over. Right? So therefore, it returns the right answer. But if each thread has to run longer, the longer it runs, A, it might run out of its quantum, which at 1,000, that's not the case. But B, other stuff on the computer that's going on may force the OS or cause the OS to yank you even before your quantum is finished. Okay? All right. Now, I want to do one thing. I'm going to close with this. I'm going to recompile this with maximum optimization. G++-03-std equals C++11 experiment. And now let's run it. Right, 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 right. Is that because, now a question to you, which I won't answer today. I want you to think about it. Is it because the optimizer somehow produces better code, or maybe it makes it so fast that the operating system never gets a chance to preempt you? Or is there something else at play that's also interesting, fun, and worth talking about? Hint, it's the last. Okay. All right, everybody. Once this video is done, it'll become available on the YouTube playlist. And I hope, by show of hands, has anyone seen the video already up there? So in other words, is the playlist properly created? Okay, Connor, thank you. Okay, very good. Then I'll see you on Friday. Okay. Bye-bye.
Bye. Thanks, Professor.
Thank you.
Thank you.
Noah, is anything? Nope.